So, how's it going? This is not a drill. I know that in the past when I did this series, I usually would have a video named Multithreaded Rendering, which wasn't really multi-threaded, but this is true multi-threaded rendering. So welcome. I actually recorded this video a number of times because every time I recorded it, I would then go back and edit the code, and then I'd make a little addendum. And I thought it would be best just to redo the whole thing. As you can see from the image here, multi-threaded rendering in Vulkan is not easy, but hopefully by discussing this, you can see some of the work that goes into it and understand some considerations that you can make for your own systems. Okay, so to start with, a number of disclaimers. This is just one implementation. There's a whole lot of different ways to do this. The way that you end up implementing multi-threaded rendering in your own system, first up, you may not need it, but it may be something completely different. So the thing that I'm doing here is very specific. As we can see here, it requires at least 4 swap chain images and queues, and the performance currently is a little less than what I was getting just with single threaded rendering. But my hope is that as the system becomes more complicated, it's able to absorb some of that extra workload. So with that out of the way, I just want to make one more disclaimer, and that is don't be a goblin. Now, what do I mean by this? Well, to be honest, this is probably me here, right? When we make a triangle, the next step is not to include multi-threaded rendering. But what I mean by don't be a goblin is keep an eye on the big picture, and I would not be worrying too much about specific metrics at this point. If we have something within the same order of magnitude and it's stable, then I'm happy with that. So, the concept that I'm using for this multi-threaded rendering stuff comes from CPU instruction pipelining. Back in the old days, the execution of an assembly instruction involved multiple steps. In a really simplified form, we would fetch the instruction from memory, and then we would decode that opcode, and then we would queue that up and execute it. But one of the massive optimizations that was noticed was rather than having a single process which encompassed these 3 steps, these 3 steps were actually independent of each other, so we could encode these, we could build them in hardware. So we have 3 independent hardware units which do 3 small subtasks. So first up, we can fetch an instruction, but then as we fetch that instruction, pass it over to the decode unit, we can at the same time be fetching the next instruction, and so on and so on. And so on average, we've sort of tripled our throughput. Now, the big concept here is that these units are built in hardware, and they execute completely in parallel at the same time. That's sort of the trick. So what I did is I took that concept and I applied it to the drawing process. So we have this drawing operation which has a number of little sub-steps, and we try to get those things independent of each other, and then we dispatch them all in parallel. So here's the basic idea. Over the course of rendering one frame, we do sort of 4 things. We acquire an image from the swap chain, we record draw commands, we render that image, and then we present that image. Now, this is a fully general system. For instance, we probably at this point do not need to record draw commands, and we may find later on that if we use a really generic GPU-driven system, it may be less important to record draw commands. But anyway, I'm rambling, but this is the basic idea. So what I'm doing is I'm treating the renderer like a state machine. And the different states that I can have are the different configurations within the pipeline. Let's look at state 0, for instance. Within state 0, we have what we call frame 0, and we can be acquiring an image for that frame. And then in parallel, at the same time, we can be recording draw commands for frame 1, and we can also be rendering frame 2, and we can also be presenting frame 3. And then the next logical step, once we've acquired an image for frame 0, is to record draw commands for frame... why can I not speak? Record draw commands for frame 0. And I hope that you can see this is a sort of logical collection of those permutations as we sort of step through the pipeline. In addition to that, as per the previous video, each of these frames have synchronization objects. So, for instance, when we acquire image for frame 0, that will be waiting on the render finished fence of frame 0. And when that operation is complete, that will signal the image acquired semaphore. And as you can see here, not only do we have our synchronization objects, but also these operations are completely independent of each other. So even if we didn't have a synchronization object, we've still got, I don't rely on it, but we've still got the separation that these tasks are occurring in different states of the rendering system. Also probably a good point at which to note that as part of setting this up, by the way, this is not one of those code it step-by-step videos. This is one of those explaining how it works videos. But when I was coding this up, I I took the image and image view out of the frame and put them into the swap chain. So I've got the swap chain and the frame sort of independent of each other. And the reason for that is that the frame is really a dummy object which sort of represents a bundle of state that will be used for rendering and doing stuff. And as you can see here, this is a very sort of sequential access, whereas the swap chain is essentially random access. We just say, hey, give me an image, we get an image, it's a random number. We can't rely on anything, really. So this is all well and good, but there are a number of issues that came up when implementing this system. For one thing, we can dispatch all this work, each of these 4 tasks, in parallel, but the queue doesn't like to be modified. Well, it can't be modified by different threads at the same time. So the workaround to that was actually to create 4 queues, one for each frame. This is why I said before, we need to be able to support at least 4 queues. My system can support 16 queues. Now, as a side note, although a graphics card can say that it supports 16 queues, in reality, for graphic stuff, there's only one hardware queue. So even though this is sort of emulating it in software, we don't get the extreme benefits that we would get if we actually had independent hardware queues. So there's that. Another thing is that swap chains can't be modified by different threads at the same time. Now, the issue with that, the reason that comes up, is when we come to acquire an image, that accesses the swap chain, and when we come to present, that accesses the swap chain, and we have one swap chain across all the queues, across all the frames. So we can't use the trick of having multiple swap chains. It's a bit, I mean, I haven't tried it. I don't think it works that well. The way I got around this issue is I added a mutex. It's simple. We just, lock the mutex, acquire the image, unlock the mutex. Same thing for present. Lock the mutex, submit the present job, and then unlock the mutex. Just as simple as that. Okay, the next one. Vulkan doesn't like too many image acquisitions to happen with no timeout. So when we go acquire next image, there's a timeout option, and usually I've been putting uint64 max, which is a special code for no timeout, but Vulkan doesn't like that. So let's say, for instance, that we've got 3 swap chain images, and we acquire 2 images unconditionally with no timeout. Vulkan's like, yeah, no worries. Then we come and we go to acquire a 3rd image with no timeout. Vulkan then says, well, wait a second, I've already given you 2 images, so I can't mathematically guarantee that we're going to be able to get a third image. And this could put us, actually this did, put us in a situation where the thing just hangs and doesn't do anything. It just freezes completely because there's no timeout. So my workaround for this, although theoretically I shouldn't need to do this, I did it anyway. I maxed out the number of images on the swap chain. My video card can support 8 images. So I just said, hey, give me all 8 images. I'm only going to use 4 of them at the most, but I'm just going to do that. And that made the thing work. And this is why I'm saying your mileage may vary with this system. Okay, so next thing. Only one hardware queue. I already talked about that. Okay, cool. Next thing, GPU may get clogged with non-useful work. So although it's true that we can sort of do all these things at the same time, let's say, for instance, that... Actually, you know what? I changed my mind. Looking at this diagram, this actually looks okay. I think. Let's find out. We're going to leave that. Emphasis on the may. May or may not. I don't know. Okay. State transitions are currently only defined for a full pipeline. So all these states that I've got here are totally fine if everything's all queued up at the appropriate stage. But the way I got around that was a little bit hacky. I simply put in a bunch of dummy operations to spin each of these frames up to the stage that they should be, if that makes sense. So let's have a look at how this worked. In the GitHub repo, I've got 2 versions. One which is sort of super parallel, and one which is a little more conservative. So if you're working with this and you can't support, like the parallel version is not working, there's a conservative version. It's still parallel, just not as parallel. So when I go to make my device, I need to request the appropriate number of queues. And that's as simple as just modifying these variables. So first up, I give a priority to each of the 4 queues. They're all going to be equal priority. And then I create the queue info, and I request 4 queues at that point. Okay, no problem. Then on the renderer side, after I go ahead and make that, I then fetch each of the 4 queues. Okay, no worries. And then, I come to make the naming here could be a little better, but basically I make 4 frames. There we have. And I'm putting in a whole bunch of info because I want these function calls to be contained. So for instance, down here, when it comes to these stages, I don't want to have functions where I'm passing in extra info. I want to keep that as lightweight as possible. And I want to keep, spatially, I want to keep all the data as close to the action point as possible. And I measured this does make a difference. So first up, we create the frames. Then we sort of spin each of the frames up so they are in the appropriate position, ready to go for their state. And then what I'm doing here is I'm recording ahead of time all of the independent jobs. Just a side note, the way I implemented this parallelism is with a library called TaskFlow, which I have talked about a number of times on this channel, or a small number of times at least. So TaskFlow is a threading library which lets you sort of define, the classic use is to define task graphs. So we can have a dependency, one task depends on another task, but also tasks can run at the same time. And if you just throw in a bunch of tasks with no dependencies, no dependency info, then by default they'll all run in parallel when the stuff is dispatched. It's as simple as sort of throwing on a bunch of lambdas. These are the independent tasks. If we were to run this right now, A, B, C, and D would all run at the same time in parallel. We can also define, links and things. But the basic idea is we just run that, wait, and it's just, even if I'm doing simple things, this is just a really neat interface to do multi-threading. So TaskFlow is very, very good. But all I'm doing here is I'm pre-recording a bunch of multi-threaded jobs, and each of these jobs represents the state diagram that I had before. So we've got that. When it comes to drawing, we simply pick the appropriate job, dispatch it, wait on that, and then increment our state timer, basically. Cool. Now, in terms of how this stuff works individually, it's pretty much copy-paste from the previous video, I think with a few minor modifications. I mean, just the semaphore stuff, so locking and unlocking to make sure we're not accessing from multiple threads. But I've kept you in suspense enough. It's not super exciting, it's just a triangle, but I guess the fact that it works is pretty cool. Alrighty, so here you go. So for one thing, our CPU usage is up. That's good. That means, yeah, we're multi-threading. For another thing, our frame rate is pretty good. Not that frame rate is the only issue. I mean, I'm running in debug mode, right? But it is a metric, so that's important. And most importantly, I guess, it's working with no errors. And we can go ahead and close that, and no errors. It's all fine. And just to verify that this is in fact, I mean, you guys trust me, right? But just to verify that it is actually working in parallel, if, for instance, I take off some of this semaphore stuff and run this, then we'll now get a bunch of errors squawking at us saying, hey, we've got this swap chain, but you are accessing that swap chain from multiple threads at the same time. So Vulkan is a multi-threaded API, but multi-threading rules still apply. Okay, now that's that. That's pretty cool. Let me bring up the other one, the more conservative version. So in the more conservative version, I'm still doing multi-threading, but instead of splitting things into 4 independent tasks, I'm grouping them together a little bit, and I've just got 2 independent tasks. The first task, I've roughly grouped it by like CPU stuff and GPU stuff. So the first task is to both acquire an image and record draw commands, and then the second task is to render and present that frame. So this is trying to make sure that the render job gets queued up directly next to the present job in order to, I don't know, to see what happens. Now, just a little note on image acquisition, because image acquisition is both CPU and GPU. Image acquisition does 2 things. First of all, it gives you the index of an image, and secondly, it acquires that image. Now, here we go, go over to the frame. We have this acquire image, and that directly gives us a result straight away. That's the CPU component, the return component. But then we signal a semaphore, and this semaphore is signaled when that image is transitioned or whatever needs to happen so that it's ready to render to. So we have like a quick return and then an asynchronous return. But anyway, how does this perform? Well, I think we had like 5,300 before, and yeah, what, 5,000, 5,100, something like that. So, like I said at the beginning, there's no hard and fast way to do multi-threaded rendering. I've seen a bunch of other implementations where the whole thing's basically all together, like single-threaded, the rendering and presentation stuff, the queue submission, but then in the background, like you have a background thread recording command buffers selectively, like only recording at certain points or things like that. There's heaps of ways to do it. But hopefully, this discussion has been useful. Cool. And that is it. So congratulations. We got this stuff working. I don't know why I'm saying congratulations, but there it is. And as our next step, we're going to be recreating the swap chain. Hope to see you there. All right. Have a good one. Bye.